Hello friends, last class I discussed about the excitonic transport, how exciton can transport and how exciton can generate at the interface, and after generation, after dissociation of the exciton, how exciton can produce the free carriers. And if you want to generate a free carrier inside the organic device, how can you produce the free carrier by injection process or by dissociation process? These things we have discussed on the last class, right? So next class onwards I will discuss about the working principle of the different kind of the organic electronic based devices. Today some points I want to discuss, that is the transport mechanism and its effect. Okay, so I told that so electron can transport and exciton can transport. How the exciton can transport and how an electron can inject into the free carriers, into the devices. Okay, so after injection of the electron, how electron can transport in through the devices. Okay, so in case of the normally if you see, this is the organic semiconductor, this bonded with each other. So this is one molecule and this is another molecule. Okay, so normally this electron can, suppose this is the HOMO level. Okay, this is the LUMO level. So this is defined as a HOMO level. This is defined as a LUMO level. Okay, this is the one band. This is the another band. Lowest occupied molecular orbital, highest occupied molecular orbital. Okay. Now in case of the normally in case of the any kind of the devices, there are the two interaction. One is the intermolecular interaction, another is the intramolecular interaction. Okay, intramolecular interaction means the one electron can move from one location to another location in a one molecule. Okay, that is the intra. So that is the inter. Okay, next is the intra. In case of the organic semiconductor, so due to the disorderness of the organic semiconductor, this is called as a disorder organic semiconductor, right? In case of the disorder organic semiconductor, normally these are the carbon compound, consist of the carbon compounds, right? In case of the carbon compounds, these organic compounds, so electron, there is a delocalization of the electron, so electron cannot confine in a one location. Okay, it has to move from one molecule to another molecule, so that is due to the delocalization. It is the nature of the electron in the disordered materials. Okay, so in case of the organic semiconductor, that is the disordered organic semiconductor, right? Disordered organic semiconductor, so there is an intramolecular interaction. Okay, so electron can transfer from one molecule to another molecule. Suppose here is the electron, this can transfer from one molecule to another molecule. Okay, this mechanism and this process is called as the hopping mechanism. So electron can hop from one molecule to another molecule. Okay, so the how the electron can transport through inside the organic semiconductor based devices. So there is a hopping mechanism. Hopping mechanism is the main dominating factor in case of the organic semiconductor, right? So if you want to get the current, okay, if you want to get the current through the organic semiconductor, the current is, that is the current mechanism or transport mechanism or conduction mechanism, right? The conduction mechanism, that is mainly driven by hopping mechanism of electron from one molecule to another molecule. Okay, this is the mainly hopping mechanism is the mainly dominating factor, right? Now hopping mechanism, that means electron can hop from one molecule to another molecule in organic semiconductor. Then in any devices, right, in this is inorganic device or organic devices, so we normally told conduction mechanism is defined by three different factors, right? One is the thermal resistant thermoic emission, another is the tunneling mechanism. So first is that means the how electron hop. So different to the structure, interlayer structure and band diagram, band bending is there. Due to the band bending and depends on the other factors also. Two mechanisms are mainly applicable in case of the organic or inorganic materials. Okay, one is the thermal resistant thermonic emission mechanism. Another is the tunneling mechanism. Okay, so normally in case of any devices, if we apply the electric field or if we apply the temperature, okay, so the some internal the structure of the devices that can be altered. Okay, to due to this the electron cannot transport so fast, or electron cannot, sometimes electron can transport slowly. Okay, so due to that we will get some kind of the behavior in the current. Okay, so one is the thermal resistant thermal emission, another is the tunneling mechanism. These two mechanisms are available. That means if I, so when the electron can move from one molecule to another molecule, we will get current. But the current, the behavior of the current, that is normally depending on the two mechanisms. One is the thermal resistant thermoic mechanism, another is the tunneling mechanism. Okay, so I am not going to discuss about these two mechanisms elaborately. So these two mechanisms are mainly main factors, right? So normally, suppose the electron. Now come to the mobility. Okay. So mobility, this thing, the below of the mobility, okay, of electron, this thing is normally related with these two mechanisms. Okay. Now, what is the mobility normally we define? The mobility means the how electron can transport from one molecule to another molecule. Okay, so the nature of the, from the value of the mobility we can define that the transport of the electron is fast or slow. Okay, so some scattering effect is also there. Due to the scattering effect, due to the trap state, the we will get a less mobility from any kind of the devices. It depends on the device materials. Okay, normally in case of the, due to the disorder and due to the hopping nature of the electron in organic semiconductor, we will get the low mobility in case of the organic semiconductor. But in case of the crystalline and pure semiconductor, inorganic semiconductor, if we calculate the mobility, we will get the high mobility. Okay, this is the one of the drawback in organic semiconductor, because we will get the low mobility. If we get low mobility, so if we are using some materials which having low mobility, we will get a less response or less speed. Okay, that's why the research is going on. We have to use the such kind of the materials from where we will get the high mobility, right? So the mobility, so normally there is a transition. Okay, so from the IP curve we can calculate the mobility and we can identify the transition, how many mobility mechanisms are there. Okay, there is a transition. Okay, transition between phonon assistant mobility at high temperature, another transition between phonon assistant mobility at high temperature and mobility field assistant mobility at high field. So the organic semiconductor we get a two different kind of the mobility effects. Okay, mobility effects inside the device, any kind of the devices on it. So that's why I told that there is a transition between phonon assistant mobility at high temperature and the field assistant mobility at high electric field. Okay, so if we see the IB curve, we will get this kind of the mechanisms. Okay, so normally when this field resistant mobility we will get. Okay, so if we apply the high electric field, that means if we apply the high voltage inside the device, that means we will get high electric field. Okay, in case of the high electric field, that means in case of the high electric field, this tunneling mechanism is the dominating factor. Okay, In case of the high electric field, tunneling mechanism is the dominating factor. So if we apply the voltage, so some band bending or some the band structure is changed. Okay, the energy level diagram is changed. Okay, so then we will get a tunneling mechanism. Okay, tunneling mechanism starts to dominate, right? So due to this tunneling mechanism, so whatever mobility we will get from the device, okay, that is a field assisted mobility. Okay, and for the other cases, normally we will get the phonon assisted mobility. Okay, at a high temperature means normally at room temperature we will get the phonon assisted mobility, right? So this is the transport mechanism, how the electron transport inside the device, and how we will get the different kind of the mobility inside the device. Now the transport mechanism, that means the mobility, due to the band change in the band structure, we will get a different kind of the current, okay, from the organic devices. Sometimes we will this current, okay, is changed due to the some other effects or due to the surface morphology of the structure. So that means next is the surface morphology affects the transport mechanism. The surface morphology, that will indirectly affects the mobility, which in turn affect the charge transfer mechanism. If you get different mobility, that influence the charge transfer mechanism. Okay, that means if high mobility will get the high current, if low mobility will get the low current, and the different kind of the behavior we can see inside the current IV response. Okay, how the charge surface morphology can affect the transport mechanism. Okay, now normally I am considering suppose one material, that is a pentasone. This is one kind of the organic material. I am considering one material. Okay, the orientation of the material, how we are depositing the material on the substrate, the orientation of the material, that also affects the surface morphology. Okay, now suppose this is a substrate. Okay, normally suppose pentasone. Okay. Okay, so this is a one orientation, and this is a one orientation. Okay, there is an intermolecular distance. Okay, this is suppose this is an intermolecular distance. So electron can transfer from one molecule to another molecule. This is suppose the D. Okay, so intermolecular distance, that affects the charge transfer mechanism. If you are getting the large intermolecular distance, or this is also okay. If you getting large intermolecular distance, normally, so we will get a low mobility. Okay, suppose in this case, I am first telling about the this condition. Okay, in this case, suppose we have deposited the molecule or material in such a way that the orientation of the molecule, that is parallel with the substrate. Okay, in this case, we will get the low intermolecular distance. That means the if you place the material in this way, so will the hopping distance between one molecule to another molecule, that is decreased. Okay, suppose that is decreased. So this is the distance, hopping distance. Suppose this is the hopping distance, that is decreased. Okay, this distance is decreased. Okay, due to the decrement of the hopping distance, decrement of hopping distance, okay, we will get a high field effect mobility. Okay, that means here we are getting the high mobility. Due to the high mobility, we will get the good response and good transport phenomena, right? So if you place the material, the orientation of the material, that is the perpendicular to the substrate. Okay, suppose if electron want to transport from this transition to this transition, or this transition to this transition, from this location to this location, or from this to this location. Okay, in this case, normally the hopping distance is more. Okay, hopping distance is more in this case. Okay, so that means here we will get the low mobility, right? So low mobility means the it affects the charge transpose mechanism. Okay, and we will get the low current. So that is how I am depositing the material. That also influence the surface morphology, which in turn influence the mobility effect, value of the mobility. Okay, so due to that we will get a less response or high response, right? This is about the transport mechanism and how it is impacted by the other parameters. Now, after that, as I told that next class I will discuss about the different kind of the devices. If you want to design different kind of the devices, okay. So in case of the any kind of the devices, suppose if you want to make diode, okay. One is the cathode, anode, and the active layer, metal layer and the active layer. These layers are required, okay. Suppose one. So normally diode consists of p-type material and n-type material, and one is the anode, another is the cathode. These four layers are mainly required if you want to design any kind of the optoelectronic devices. To increment the different kind of the parameters, to increment the performance, we can add the more layers and we can compose the different kind of the materials, right? So we can design, you can use only one active layer or you can use the two active layer. If you use the two active layers, that is more efficient, right? P-type material and N-type material. Okay, so we have to understand the transport level. Okay, so how we have to decide that which p-type material is suitable for n-type material, that I will discuss elaborately on the next coming lectures. Okay, now normally suppose this is the transport level. Okay, suppose this is LOMO 1 and this is the LOMO 2. Okay, so whatever p-type material if you want to choose, okay, so the LOMO level of the p-type material, that corresponds to 4 electron volt. Okay, so you will 3.5, 3.8, 3.9, 4, 4.1. So LOMO level should be, okay, nearly equal to the 4 electron volt. Okay, and why these things I have to choose, that I will tell. Okay, so normally the maximum organic semiconductor, p-type organic semiconductor, such kind of the LUMO levels are there. Okay, and this LUMO 1, that is the LUMO of the p-type semiconductor, that should be lower than the LUMO of the n-type semiconductor. And whatever n-type organic semiconductor you will choose, maximum organic like 4.5 to 5 electron volt. Okay, this is 3.5 to 4 electron volt. Okay, after choosing this 4, and other parameters are also required if you want to choose the p-type and n-type material. This is the normally, this is the position of the LOMO level of p-type semiconductor and the n-type semiconductor. This is normally 5 to 5.5 to 6 electron volt. This is normally 4.5 to 5 electron volt. Okay, this should be higher. This LOMO 2 and HOMO 2, they should be higher than this LOMO 1 and HOMO 1. Now, after choosing this p-type and n-type material, okay, we have to choose the anode and cathode. Okay, how we will choose the cathode? Okay, the work function of the cathode, that should be matched with the LUMO of the p-type material. Okay, normally we can choose the aluminum, okay, right, and silver. Okay, this is with the material 4.1 electron volt. Okay, 4.1 electron volt. So normally the electron transport through the LOMO level, right? So the barrier gap between this LOMO 2 and the cathode, okay, there should be very less for electron injection from cathode or electron transfer from LOMO to cathode. The electron can transfer either this way or electron can transfer from this way. Okay, due to this we have to choose the cathode in such a way. The energetic gap between LOMO 2 and cathode is very less, right? So for case of the anode, so the normally the hole will transport through the HOMO level, right? The hole can inject from anode to into the device, or it can transfer from device to the hole, device to the anode. Okay, so this gap should be very less. Upon hole, that is normally ITO, indium tin oxide, or gold you can choose for as a anode. Okay, I2, if you choose the I2, that is a transparent layer. So if we choose such kind of the anode, so this energetic gap is very less, right? So next class I will discuss. I will start. I will start discussion of the organic light emitting diode. Thank you.